Okay, morning everyone. My name is Martin Bridson. I'm the president of the Clay Math Institute. I just want to say a quick hello to everybody. Thank you for coming. Welcome to the Clay Research Conference 2024. This is the highlight of CMI's year, our great celebration of contemporary mathematics. And looks like it's going to be a great day of mathematics, from which I shall not detain you any longer. I'll ask Andrew Wiles to introduce our first speaker.
Hello, it's my pleasure to introduce Anna Caraiani today, who I first met when she was in first year at Princeton, did a senior thesis with me, and went on as a graduate student at Harvard, and since has had positions in many places, but is currently professor at Imperial and a Royal Society University Research Fellow. Her specialties have always been in number theory. I like to hope I had some influence on that. She specializes now in geometry of Shimura varieties and p-adic representations, and in the Langlands program more generally. She's recognized for great contributions she's made in these fields, and has won a number of prizes, most recently the New Horizons Prize last year. She's a wonderful speaker for a general audience too, as we know in Oxford already, and I'm sure you're going to enjoy a wonderful talk today about the Langlands program.
Thank you very much for the introduction, and thank you to the Clay Institute for the invitation to speak, but also for the, so I'm also one of the organizers of the Clay Research Workshop, and I'm very grateful for the opportunity to have been able to organize this workshop around the Clay conference and, bring a lot of exciting people from all over the world here in Oxford for this week. And so the topic of our research workshop is the Langlands program, which is sort of a web of conjectures that are meant to connect different areas of pure math. For example, harmonic analysis or representation theory to algebraic number theory and arithmetic geometry. And a really famous instance of the Langlands program is the modularity of rational elliptic curves, which was the key to Andrew Wiles's proof of Fermat's last theorem. But sort of for this talk, I decided not to focus on modularity, but instead to focus on some really fascinating geometric objects that sometimes give you a concrete kind of explicit geometric realization of the Langlands correspondence, and these are Shimura varieties. So I want to tell you just about these fascinating geometric objects and their many symmetries. And the reason that I decided this was that there's been a lot of recent progress in the area, a lot by people who are in this room now. And towards the end of my talk, I want to try and give you some high-level view of how the different talks at the workshop this week connect with each other, but in a way that is still hopefully interesting to a general mathematical audience. And so to begin with, so I want to tell you about Shimura varieties. So the global Langlands correspondence is supposed to match up different kinds of data that show up in very different contexts. And on the more harmonic analysis side, what you see in this data are systems of eigenvalues that show up from the geometry or the topology or the analysis of certain highly symmetric spaces. And that's the perspective from which I want to approach Shimura varieties. And then later on the arithmetic side of the Langlands correspondence, you see the kind of data that comes from counting solutions to polynomial equations, modular primes. So that will come up later. But for now, I want to talk about spaces with a lot of symmetry and that know about interesting systems of eigenvalues. So I want to start out with a group. These spaces are going to be attached to groups G over Q a connected reductive group. So if you don't know what that is, don't worry about it. So take the example of GL2, so 2 by 2 matrices. With coefficients in the rational numbers, you can carry this throughout the talk. Or SL2, 2 by 2 invertible matrices with GL2, and SL2 is 2 by 2 matrices with determinant 1. So either of those examples, you already see some structure, and in fact, I'll talk about these examples in detail in the next couple of minutes. But I want to give you kind of the general picture, and then we specialize to these examples. So I want to look at the so-called symmetric space for the real points of the group. So this is a real manifold. It's endowed with a Riemannian metric. And so for me, I can just take as a definition quotient of the real points of the group by maximal compact subgroup, and possibly also by some torus part that's just used to get kind of finite volume spaces at the end. So not something to worry about. It's kind of technical. Okay, so I want to look at this, and this just knows about the group as a group over the real numbers. But in the Langlands program, we ultimately want to connect things to arithmetic, and so I care about the fact that I started out with something that had a structure over the rational numbers, if it was these, 2 by 2 invertible matrices over the rational numbers. And so you look at this real manifold, but you want to form something called locally symmetric spaces that are obtained by taking quotients of this real manifold by certain groups that are arithmetic groups. So this X, by construction, has an action of the real points of the group. And inside here, I could take an arithmetic group. For example, if my G had a model over Z, I could look at the integral points. So 2 by 2 invertible matrices, but with integral coefficients. That's an example of an arithmetic group. And Shimura varieties are very roughly some very special kinds of locally symmetric spaces, which are quotients. So we form the locally symmetric space X mod gamma. If gamma is taken sufficiently small, so maybe in addition to just taking like the integral points of my group, I impose some additional congruence conditions to cut out my matrices a little bit. So for instance, I ask that one of the entries is divisible by 3 or something like this. So if I make it smaller, then I can ensure that this locally symmetric space has the structure of a smooth real manifold. Okay. All right. And so as a first approximation into the world of Shimura varieties, you want to think about kind of the real symmetric space for your group, quotiented out by an arithmetic group. And then Shimura varieties are special kinds of these objects that happen to have additional structures. But before I go into that, I want to talk about one kind of structure that these symmetric spaces have that is called Hecke symmetry. And that is something very general that shows up even before you start talking about Shimura varieties. And so in order to do this, I need to do something a little bit technical for a second, but then I'll explain why, in fact, it's not really that bad. So I want to take the finite adelic points of my group. So I thought about the group over Q, over this global field. Then to form the symmetric space, I thought about its real points. And now I want to take some kind of restricted product of the group over the other completions of the rational numbers, which are the p-adic points. And instead of taking an arithmetic group, it turns out that it's essentially equivalent to take a compact open subgroup. So this has a topology, and it's essentially equivalent to take a sufficiently small compact open subgroup inside these finite adelic points. And I want to define my more general version of a locally symmetric space, instead of just as a simple quotient, as a double quotient, where I take the real symmetric space times this information that knows about all the finite primes. So here P runs over all the finite primes, and then quotient out by the level on one side, and quotient it out, that's where arithmetic comes in again, so quotient it out by the rational points of the group. Something like this. So it turns out that this is not too far apart from just taking a disjoint union of quotients like I had above. And that's because it turns out that there are finitely many double cosets. So if I take this group and I want to write it in terms of double cosets, then this is disjoint union over a finite set of the rational points, some coset representatives, and then this compact open subgroup at the finite adelic points. So this is a kind of approximation result that vastly generalizes the Chinese remainder theorem. And because of this, we can write xk as a disjoint union over I in this finite set of x quotiented out by gamma I, where gamma I turns out to be an arithmetic group. So this is the intersection of gamma I inverse, gamma I, k, gamma I inverse. So up to just taking a finite disjoint union, this bigger locally symmetric space that I considered here is essentially just this kind of object. So this kind of object is useful because it's concrete. And I'll write down explicit examples in a second. But this kind of object is useful because you really see the full force of kind of the kinds of symmetries that you're allowed to have. So as it turns out, the right thing to do is to consider the limit, the inverse limit of these objects as this group gets smaller and smaller. So I can take a smaller and smaller compact open subgroup at some prime or at all primes, well, at finitely many primes, and I can consider the limit. So we can consider the inverse system of spaces like this, where K runs over compact open subgroups. And the advantage, so the symmetries that start showing up, is basically this inverse system has an action of this entire finite adelic group. So it has an action in particular of GQP, so the p-adic points of your group, for every prime P. Right, and this gives rise to one kind of symmetry that shows up in the Langlands program and in the study of Shimura varieties, which is the so-called Hecke symmetry. So this action, and the way that we want to really think about it is we want to think about it on cohomology. So the inverse system of spaces, there's a way to take an invariant attached to each space that remembers its complexity. That's the cohomology of the space. And you can think about it as just the singular or Betty cohomology of the real manifold. And this inverse system of spaces kind of covering each other gives rise to kind of a directed system of these cohomology groups. So these cohomology groups are vector spaces, maybe graded by the degree. And so this is a directed system. So the cohomology groups get bigger and bigger. The complexity gets bigger and bigger. And on this, you still have a representation of this giant finite adelic group. And in particular, you have these p-adic representations. OK, you can remember the Hecke symmetry at finite level through the action of a Hecke algebra. So if you, instead of considering the whole system of spaces, which in the limit looks kind of like a solenoid when you let the compact open subgroup get smaller and smaller, if you just want to look at some fixed finite compact open subgroup, then there is a way to remember that you had the whole system and you had this whole symmetry in the picture by taking certain averaging operators. So this is an algebra generated by averaging operators called Hecke operators. Okay, so this is kind of, in some sense, the technical part. Now we just make it explicit. So as I said, it's enough to consider really one example. I'll give you, in fact, one example, one non-example, and then I'll mention the general case. So that's what I want to do now. So the first thing is, as I said, maybe you don't have to worry about a general connected reductive group. You already see some interesting structure if you start out with GL2 over Q. The symmetric space for GL2 over Q, you just plug in the definition. So the maximal compact, if I take the connected component of the identity, it's an orthogonal group. And then I have to quotient out by some torus part, which is just technical. And it turns out that you can identify this with a copy, so with upper half complex plane and lower half complex plane. So you take the complex plane and you remove the real line. So the disjoint union upper and lower half complex planes. So Z in C with the property that the imaginary part is positive or the imaginary part is negative. So it turns out this has an action of GL2R by so-called Möbius transformations. There's a standard formula where you write down a matrix A, B, C, D in GL2R will send Z, so if this is gamma, then gamma sends Z to AZ plus B over CZ plus D. And you can check that this property of avoiding the real line is preserved under this action by transformations. And this is exactly the stabilizer of a point, and this is how you can write your union of upper and lower half plane. This is how you can identify it with this symmetric space for GL2R. Okay, and I can even, to make things more concrete, I can draw a picture of what the locally, so this is the symmetric space, I can draw a picture of what the locally symmetric space looks like. So first of all, the xk are, by this approximation result, disjoint unions of just H mod gamma, where gamma in SL2Z is some finite index subgroup that's cut out by congruence conditions. So it's a so-called congruence subgroup. And so you just look at, you restrict the action of GL2R, or maybe if you look only at one component, so H plus, then you look at SL2R and you restrict this to SL2Z or to a finite index subgroup in there and take the quotient. And essentially, like sort of from a geometric point of view, this is what the locally symmetric spaces look like. In this case, there is a famous picture I want to draw. So this describes the action of SL2Z on the upper half plane. SL2Z is generated by 1, 1, 0, 1, and by 1, 0, 1 minus 1, 0. And so the effect of 1, 1, 0, 1 from this formula is just taking z to z plus 1. So if I want to understand what's a fundamental domain for this action on the upper half plane, I can just restrict to a strip of length 1, and I can take the one that's symmetric about the imaginary axis on the complex plane. So translation by 1 is what one of these elements does, and the other one is close to inversion about a circle. So the circle is the one of radius 1, centered at the origin. So this is 1 minus 1. They intersect at a cube root of unity, sixth root of unity, and cube root of unity. And if you want just a fundamental domain, so if you want to understand what part of the upper half plane kind of is enough to then translate and understand how SL2Z acts, that's the fundamental domain here. The quotient you form by also identifying pieces of the boundary. So the H mod SL2Z looks like the fundamental domain, but with pieces of the boundary identified. And it ends up looking like a punctured Riemann sphere. So there's a kind of a cusp that goes off to infinity that corresponds to this imaginary axis going off to infinity. And then there's some kind of funny orbifold-like points around the roots of unity where you have some fixed points. So there's rho, and there's one around I, which is over here. OK, if you take some finite index subgroup cut out by congruence conditions, what you're going to get is a bigger space that covers this one. And if it's sufficiently small, then these points that are funny, that are not quite smooth, are going to get smoothed out when you look at the cover. So maybe a cover looks something like this. And this is my H mod gamma. Maybe I have more than one cusp. But kind of the funny points have been smoothed out. And you should really think that you have a whole inverse system of these. And you have to consider the various symmetries that you get by the different ways in which you can project from higher up in your system to lower down. So this kind of action of, say, SL2QP or GL2QP on the inverse system of all the spaces where you take all possible finite index subgroups. OK, so this is a locally symmetric space. But this is even more than that. So there's something special that happens in this particular setting, and that's going to be our connection to the world of Shimura varieties. So these are not just real manifolds. There's a complex structure on the upper half plane, and this complex structure can be descended to the quotients by these arithmetic groups. So it can be descended to the locally symmetric spaces. So these are actually Riemann surfaces. And in fact, more happens. So you can compactify them in a nice way because you can understand the cusps. And then you can show that they really come, so they don't just come, they come from projective curves over the complex numbers, but something even more special happens in this case. They come from curves that are cut out by equations that have rational coefficients. So they are really the underlying Riemann surfaces that you get by starting out with curves that are cut out by polynomial equations with rational coefficients. So they come from curves over Q. They have models over Q. So models over Q, let's say we call these SK. So the SK are really curves over the rational numbers that give rise to these Riemann surfaces. And so the complex structure and the fact that there is an equation over the rational numbers, so we're kind of back to seeing some arithmetic in the picture, that's something that's really special. And whenever this happens, that's essentially when you have a Shimura variety. So roughly speaking, Shimura varieties are locally symmetric spaces, but that have the structure of varieties defined over the rational numbers or over finite extensions of the rational numbers. That's going to be my sort of working definition of what is a Shimura variety. With sort of that have an algebraic structure. With an algebraic structure. And the effect of this is that they don't just have the Hecke symmetry that comes from having these towers of locally symmetric spaces, but if you look at a related invariant, a cohomology theory for algebraic varieties, then you also have a Galois symmetry. So a cohomology theory for algebraic varieties is the Étale cohomology introduced by Grothendieck, I guess about 60 years ago. And this is meant to be well-behaved, kind of like the cohomology, sort of singular and Betti cohomology for topological spaces, but it's for algebraic varieties, and it should compare well with Betti cohomology. And in addition to this, it's something that remembers. So when you start out with a variety that's cut out by rational coefficients, it somehow remembers this. So we take our curve defined over the rational numbers, but then we want to view it over an algebraic closure of the rational numbers. So we adjoin kind of algebraic numbers that have lots and lots of symmetries. And then this cohomology theory gives you a vector space that has an extra symmetry that remembers the fact that our curve came from the rational numbers. And I'll give you a concrete example of how you can realize this in a certain case. So this has, so if I take the limit over k, this has the Hecke symmetry, but it also has an action of the absolute Galois group of the rational numbers, and that's a Galois symmetry. So this is remembers all the symmetries of algebraic numbers. It's a huge profinite group, but sort of our vector space comes with some representation of this group and gives you a way to sort of try to understand this group. So there's a Hecke symmetry, and there's a Galois symmetry. And so that's what's special about these spaces, and that's one way to kind of get started with the Langlands, sort of understanding the Langlands correspondence, is to consider one of these cohomology groups where both kinds of symmetries show up, and then you can hope to relate. So from the Hecke symmetry, you can look at systems of eigenvalues for these averaging operators, and that's the kind of spectral data that I talked about in the beginning. And on this side, from the Galois symmetry, you can extract arithmetic data. And so this, in this particular case, this Shimura variety is called a modular curve, and this modular curve realizes one instance of the Langlands correspondence where you go from the Hecke side to the Galois side. And let me actually be more explicit. Yeah, I start a new board. So if f is a cusp form, so a modular form, a holomorphic function on the upper half plane that has lots of symmetries with respect to the action of gamma on the upper half plane, but that vanishes towards the cusp. And for technical reasons, I'll say weight 2. Maybe that's not something to worry about too much. It contributes to the cohomology of the modular curve. Let me just define this to be H star, and then if I want to go back to some finite level, I'll put H star sub k, and it contributes to H star, or maybe Hi, in degree I equals 1. So this is a curve. It doesn't have that many cohomology degrees, but it has an H0 and an H1. And it turns out that the special kinds of modular forms that vanish at the cusps and that are more sort of naturally the ones that genuinely come from the group GL2, those are the ones that contribute to cohomology in degree 1. And moreover, H1 for some special level k that's chosen to be minimal. So maybe if I cut out some system of eigenvalues, so if F is an eigenform, simultaneous eigenvector for the Hecke operators, and I take out the system of eigenvalues corresponding to our form F, this can be identified with an arithmetic object that is intrinsically attached to F, which is the so-called Galois representation attached to F. So this is a representation of the absolute Galois group of Q, and it's two-dimensional, and it's valued in this field of L-adic numbers, or maybe an algebraic closure of it. Okay, so Shimura varieties have these two kinds of symmetries, and they know about each other, and they can be used to construct some instances of the Langlands correspondence, going from the Hecke or automorphic side to the Galois side. And before I move on, I also want to tell you, okay, this curve also has an H0, this modular curve. And the interesting forms show up in degree 1, which is the middle degree of cohomology, but you can also describe H0 of the curve. In this case, you can compute it explicitly. So at some finite level k, if M in here, if some system of Hecke eigenvalues occurs in H0, then it turns out that the representation, there's still a Galois representation attached to it. There's a two-dimensional one. But this is somehow degenerate. So this has the form chi, a character, times 1 plus the cyclotomic character, where chi is just some finite order character of the Galois group. And where the cyclotomic character is a very particular one. So this goes to the absolute Galois group, to the Galois group of the extension of Q. It factors through the Galois group of the extension of Q that you get by adjoining all Lth power roots of unity. So if I adjoin Lth roots of unity and I look at their symmetries, this is going to be a Z mod L minus 1 Z. In general, if you adjoin sort of powers, well, if you adjoin all the Lth powers, you can identify this with the integers in ZL, in the ring of L-adic integers. And so this is a very special kind of character. And explicitly, if P is a prime that is different from L, then there's some element in here that will remember this prime P. And if I evaluate my Galois representation, my two-dimensional one, at this element, then what I get is a matrix with eigenvalues alpha, where alpha is something. We don't know necessarily what it is, but the point is that you see this sequence of eigenvalues, alpha and alpha times p. And that's because of the effect of this Frobenius at p, that what effect it has on elf power roots of unity. Okay, so the takeaway here should be Shimura varieties have these two kinds of symmetries. Their étale cohomology sees both of them and gives you a way to realize the Langlands correspondence explicitly. And then also, if you look at the range of degrees that you can see in étale cohomology, the middle degree is interesting and sees the most non-degenerate forms, and degrees further away from the middle degree start to see some degeneration. And this kind of degeneration you can mentally think of as sequences of eigenvalues where you keep multiplying by p if you evaluate on this kind of special element that knows about the prime p. So even more roughly, takeaway is cohomology in the away from the middle degree starts to become degenerate. So before I start discussing this in more detail, I want to give you a non-example of a Shimura variety. So maybe, yeah, my first example was 1, and this is 2. So you can't always start with a locally symmetric space and get this algebraic structure. I want to convince you that this is actually quite special. And so let's take F to be a quadratic, an imaginary quadratic field. So d is greater than 0, n square free. This is an imaginary quadratic extension of the rational numbers. And I want to take, for my group, SL2 over F. There's a way to view this still as a group over the rational numbers. And then the associated symmetric space, so this is the symmetric space for G of R, this ends up being identified with SL2C, quotiented out by SU2. And if you look just at what the dimension of this quotient might be, you see that it has real dimension 3. In fact, it can be identified with hyperbolic 3 space. So instead of doing GL2 over Q or SL2 over Q, if I do SL2 over an imaginary quadratic field, and I want to look at the associated symmetric space, I get something that doesn't have a complex structure, it doesn't have a hope of having a complex structure because it has this real odd dimension. And so in this case, the xk's are arithmetic hyperbolic 3 manifolds. And they don't have a canonical structure as algebraic varieties. So the general case of locally symmetric spaces is like this. But somehow the algebraic structure and then this direct connection to arithmetic is something very special. And that says that Shimura varieties are really very special. And it's more of an accident when you have a Shimura variety than when you don't. So if I took GLN over an arbitrary number field, then the locally symmetric spaces would not have an algebraic structure. And that's one of the big kind of obstructions that we face in the field now, is how to understand what the Langlands correspondence does in those contexts. Okay, so this is one example. This particular case where you start out with an imaginary quadratic field is also called the Bianchi setting. But GL2 and SL2 are not the only groups that give rise to Shimura varieties. There are other groups. And so one way to generalize this is to consider GSP2G over Q as your original group. And then in that case, you do get Shimura varieties. And the SK, so the thing that made you really have a model over the rational numbers was that these modular curves represent a moduli problem of elliptic curves with extra structures. And in this case, the corresponding Shimura varieties are moduli of abelian varieties of dimension G and equipped with principal polarizations. And K-level structure. And maybe to the people who are here from the algebraic geometry workshop, so maybe these are more commonly known as AG. So that's another example. Other example, so if G is a unitary group or orthogonal groups. So there are lots of groups, higher rank groups, that give rise to Shimura varieties. It's just still quite special in the whole world of locally symmetric spaces. But this is something well understood, there is a complete classification. And what I want you to think about, the general cases, so there's this algebraic structure that means you have a Galois symmetry in addition to the Hecke symmetry that just comes from the structure of a locally symmetric space. These varieties are smooth and quasi-projective and defined either over the rational numbers or just over a finite extension of the rational numbers. And often, but not always, they can be related to a moduli problem of abelian varieties with extra structures. And that's something that's very useful in the study. Like if you want to understand what their geometry looks like, you want to exploit this moduli problem of abelian varieties. The ones that can be related to this are typically much better understood than the ones that can't. So for instance, in these cases, you can talk about integral models and look at their special fiber modulo prime and study things there. And another thing is that because they have all these different kinds of symmetries, they are also good test objects for conjectures in arithmetic and algebraic geometry. So that's kind of, a lot of different structures meet on the same object, and that kind of, produces really interesting effects. So for the rest of the talk, I want to focus on one particular kind of interesting thing that you can see in the cohomology of Shimura varieties, and that is taking this principle that I talked about in the case of the modular curve, so for GL2, kind of seeing how that generalizes. So the idea that the kind of most non-degenerate systems of Hecke eigenvalues, so things coming from the Hecke or automorphic side that are non-degenerate occur in the middle degree, and then as you go further from middle degree, you should see degeneration. So this kind of is, at least when you think about cohomology with characteristic zero coefficients, is related to having a Lefschetz structure on cohomology. But really, because these varieties are not always compact, as you've seen, I want to really think about intersection cohomology. So this is a way, so the varieties are smooth and quasi-projective. And if you want a cohomology theory that is very well behaved, for example, that satisfies Poincare duality in this setting of varieties that are smooth, quasi-projective, but not necessarily projective, then you can work with something called intersection cohomology. So if the Shimura variety is compact, it's just the usual cohomology, and otherwise it's a modification of the usual cohomology that somehow behaves better. It's also something that is more naturally related to automorphic representations, more naturally described in terms of automorphic representations. And so kind of conjectures of Arthur and Kottwitz from more than, say, 20 years ago, describe, sort of predict what the intersection cohomology of a Shimura variety looks like. And these apply in the case when you look at the Shimura variety with complex coefficients or with characteristic, with coefficients in some field of characteristic zero coefficients. So what this looks like. And one important thing is that this intersection cohomology actually has a Lefschetz structure. So not just Galois symmetry and Hecke symmetry, but there's also a Lefschetz structure, and there's a Hodge structure. And basically, Arthur thought about the way in which these different kinds of structures interact on the intersection cohomology of the Shimura varieties, and as a result, sort of predicted that. So all of these interact, all the different structures interacting leads to sort of the expectation that sort of I H D minus K of the Shimura variety Sk, say with QL or complex coefficients, this by the Lefschetz structure is isomorphic to IHD plus K of Sk. This is more and more degenerate sort of as K grows. So this is symmetric about the middle degree of cohomology. D is the dimension of the Shimura variety. But as you go further and further from the middle degree, you should see more and more degeneration. And if you work with coefficients of characteristic 0, then this is actually something that can be proved in many cases using, for example, results of Arthur on classification of automorphic representations. And so this can be formulated precisely. And this kind of degeneration you can sort of formulate as a global condition, or sometimes you can put local conditions at specific auxiliary primes. But the question that I want to kind of focus on for the remainder of the talk is what happens if you look at the cohomology of Shimura varieties, but not with characteristic 0 coefficients, but with torsion coefficients. So question, is there an analog? So this is really a conjecture of Arthur in characteristic 0. Is there an analog of Arthur's conjectures in sort of for the intersection cohomology of the Shimura variety, but with FL coefficients, where L is some prime, so torsion coefficients. The reason why this question is interesting, well, one is that this kind of thing has a lot of applications. And some of them have come up or will come up this week at the research workshop. So if you know that you can put some non-degeneracy condition on the intersection cohomology, if you can put some non-degeneracy condition and you know cohomology is going to be just concentrated in the middle degree, then this is something very useful for people who want to prove, say, modularity lifting theorems, the kinds that go into establishing the other direction of the Langlands correspondence. This kind of result in a sort of knowing this kind of thing in a very particular case also plays a role, for example, in the prize-winning work of Newton and Thorne on symmetric power functoriality in the specific case of Hilbert modular forms. So that's where they use something like this for a very specific Shimura variety. This kind of thing also has applications to Euler systems that are used to try to attack the Birch and Swinnerton-Dyer conjecture. So this kind of condition came up in Naomi Sweeting's talk yesterday at the workshop. And also, this kind of result, a version of it, has also played a key role in advances in kind of understanding the Langlands correspondence in this Bianchi setting, where you're working with locally symmetric spaces that don't have an algebraic structure, but in a setting that still can be related to some Shimura varieties. So for example, work of myself and Newton on modularity of elliptic curves over imaginary quadratic fields crucially used a version of this result for a particular unitary Shimura varieties. And it's going to be this kind of result is also going to be used in, or underlies what you will see in Thorne's talk on Friday on the Ramanujan conjecture in the Bianchi setting. So one answer is there are lots of applications if you know something like this. And the other answer is, well, I don't know. It's just interesting to see what the cohomology looks like in this kind of torsion setting. It's kind of within the framework of understanding what is a torsion version of the conjectures originally formulated by Langlands. So with that being said, maybe I want to end with telling you a sample theorem in the compact case, and then mention some work in progress, specifically for intersection cohomology of non-compact Shimura varieties. So the sample theorem in the compact case is the following. So we're going to assume SK is compact. And we're going to look at a system of Hecke eigenvalues. That occurs in the cohomology of this compact Shimura variety with torsion coefficients. If M satisfies a genericity condition, and I won't be precise, so sufficiently generic, this is a representation theoretic condition at a prime P different from L, so an auxiliary prime, but it's in the spirit of excluding these kinds of sequences of eigenvalues where you have one eigenvalue and then P times it occurring. That's the kind of genericity condition we put here. Then the cohomology of the Shimura variety, if I take out sort of the part that knows about this system of Hecke eigenvalues M, so I localize at this system of Hecke eigenvalues, this is concentrated in the middle degree. Which is the dimension of the Shimura variety. And I didn't attribute this theorem because sort of it's had different versions over the past decade, and each version has been better, and in each case the proof has been more conceptual. So kind of the strategy for proving this theorem in general is due to, so an original version was my joint work with Schulze that I in fact talked about at the Clay Research Workshop 9 years ago. That's the first time when I announced a version of this theorem. And then a better version put forth by Koshikawa maybe 4 years ago or 3 years ago. So he was one of the speakers on Monday. And then an even stronger, more flexible version last year put up by Linus Hamann and Xiying Li. So Xiying Li is another one of the Monday speakers. So, right, this is kind of the sample theorem. The strategy has been refined over the past decade, and at this point there's a very conceptual argument that allows you to prove this in many, many cases. So it applies, I won't get technical, but I'll just say to most, say, unitary Shimura varieties. So these are the ones that have applications, for instance, to this Bianchi setting. They're very useful to GSP4 and some other groups, although frustratingly enough, one doesn't actually know how to do the general case of AG, so Ziegel modular varieties, the ones attached to GSP2G. Although I can tell you something about that later if you want to ask me. Right, and it's had a lot of applications that I sort of verbally mentioned, and so I won't write down. The reason I don't want to write it down is because I want to say something about the very conceptual proof that we have access to now. So the proof of the theorem, maybe I put modern proof of the theorem. Uses, and this is sort of my favorite geometric object now. So this is the Igusa stack that was constructed also last year by another one of the speakers at this workshop. So Igusa stack of Mingjia Zheng, so for certain Shimura varieties, and then extended in work of Daniels, Kim, Van Hoften, and Zhang for very recently for a more general class of Shimura varieties. And this is when you work over, say, p-adic fields. So for instance, let's just go to p-adic completion of an algebraic closure of QP. For simplicity, there is a Cartesian diagram so we have our Shimura variety. I want to think about it as a p-adic analytic space, and I want to take an inverse limit where I let the level only at the prime p get smaller and smaller. So it's this kind of inverse system, but I just shrink the level at this one chosen prime p, and I view this as a p-adic analytic space. In many cases, this is known to be a perfectoid space. This has access to this Hodge-Tate period morphism constructed by Schulze, and this was very sort of important in solving a lot of problems in the Langlands program. So kind of his construction of Galois representations for torsion classes has been fundamental to all the progress that we've had to questions about modularity in the Bianchi setting, for example. But what happens is that there's a purely local arrow where this maps to an object called Ban-G. So this is kind of G bundles, stack of G bundles on the Farg-Fontaine curve. It's a p-adic incarnation of the kind of object that people who do study the Langlands correspondence in more geometric settings, for example, in the function field setting, have studied for many years. So there's a purely local part of the picture. This is well sort of understood using work of Farg-Schulze. And then what Mingjia and then this group of collaborators did was able to descend this Shimura variety, so over a p-adic field, to descend it so that this can be completed to a Cartesian diagram. So this is the so-called Igusa stack. And the advantage of doing this is that this arrow essentially gives you a way to understand the cohomology of Shimura varieties using ideas from the geometric Langlands program. So over here, for any kind of, for well-behaved sheaves over here, one has access to an action by an algebra of excursion operators that is very powerful, constructed by Farg and Schulze. And because you have this arrow, you can consider the relative cohomology of this Igusa stack and study it using this action that is now available. And ultimately, that gives you information about the cohomology of the Shimura variety. So like huge advances in p-adic geometry and connections to the geometric Langlands program are the way to get the most conceptual proof of this theorem. And then you can kind of do it in a few lines. Kind of the global input that you need is, if I call this map pi bar, is to know that the relative cohomology, so R pi bar lower star FL, is in some sense a perverse sheaf. On this object Ban-G. So I won't make it precise, but there is a precise way in which you can think of this as a perverse sheaf. And so this perversity is what ultimately gives you information about what degree of cohomology you can expect to see once you go back to the Shimura variety by doing this fiber product diagram. So you can recover limit Kp cohomology of the Shimura variety with level Kp. FL, maybe localized at M, by applying T mu to this sheaf. This sheaf I can also localize at M by applying a certain Hecke operator. It's a more geometric version. So it's like these averaging operators that I talked about in the beginning, but a more geometric version of it. And then essentially the perversity under the genericity condition amounts to some perverse t-exactness property of the Hecke operator. And that's something that lives purely within the work of kind of categorical local Langlands, but it's a local result. So T mu is perverse t-exact on generic subcategory. It's something that can be made precise. This comes from the work of Linus Hamann. Okay, so kind of there's a very conceptual proof using this Cartesian diagram of this kind of result in the most non-degenerate case. And maybe I just want to end to say that in joint work, so okay, no, before I go to this, so Mingjia will talk about the Igusa stack tomorrow. So you'll see how powerful it is and all the different applications one obtains from having constructed this. And it will show up also in the talk of Paul van Hoften on Friday. So these are, again, themes that show up for the entire week. Maybe I want to end by saying that in joint work in progress with Mingjia Zheng and with Linus Hamann, we are looking at a non-compact version of this diagram and constructing an intersection complex on the compactified Igusa stack that should recover the intersection cohomology of Shimura varieties. And that means that you should have a version of this theorem with middle degree also apply to intersection cohomology of non-compact Shimura varieties. And then depending on kind of the t-exactness properties of this Hecke operator on various subcategories, you could potentially connect kind of the relative cohomology of the Igusa stack to the relative cohomology of the Igusa stack should be some global incarnation of these Hecke eigensheaves that show up in generalized eigensheaves that showed up in Koshikawa's talk. And the shape of cohomology that one sees in Arthur's conjectures should be somehow explained by different t-exactness properties of Hecke, of this Hecke operator on kind of different, less and less generic subcategories. All right, so thanks very much for your attention. I'll stop here.